So we were discussing second law, and we had talked about two definitions of second law. One was Kelvin-Planck statement, and the other one was Clausius statement of second law. Okay. Then we came to this reversible and irreversible processes. And I told you that a reversible process is one in which the system as well as the surroundings both can be restored to their original state. Only then the process is reversible. So normally all processes which are cyclic in that system comes back to its original state. If you are moving in a cycle, the system comes back to its original state, but then the surrounding does not come. So in reality, even when the system is coming back to its original state, the process is not reversible, and reversible process do not exist. They are idealized process, and we study them because they are the best performing processes, and we can compare our normal processes with reversible processes. Okay. So this one thing you should remember, that when a system as well as the surrounding comes back to its original state, then only the process is reversible. Okay. Then I moved on to another way of explaining that what is the reversible process, and that was by way of entropy. So in terms of entropy also, we can define that which process is reversible or irreversible process. Okay. Now, before that, we have to define what is entropy. And I told you last time also that traditionally the definition which is given, that is of entropy, is that it is a measure of disorderness. Okay. Which is slightly a vague term and doesn't serve our purpose, because we cannot measure disorderness. It's a subjective term. I gave you an example that everybody arranges things in its own way, and what is a order for us may be disorder for somebody else, and what is disorder for us is a order for somebody else. If you look at a Rubik cube, it has millions of solutions, right? It is, but we always try to get a one particular solution, because in our mind that is a fact that this is a ordered way. But you take any combination, the amount of effort to get that particular shape will be same. Each one of them is in itself has an identity. The problem is that we do not recognize that. We want things in a particular way, and that is why when we go around, we go in a jungle, we said it is a haphazard way it is growing. And I gave you the example that in MNIT, they everywhere they are these fences they are cutting in a beautiful way, because the normal way which they grow, people don't like it, and that is our problem, that we don't like it. Have we asked the tree that why it has grown in that particular way? And you'll find that it has a reason. It is to capture the as much of as sunlight as possible. So we should get out of this concept of कि ये ordered है और ये unordered है और ये disordered है. Okay? This is our mental makeup which makes the thing. And this is just, as I told you, just to tell that kids कि भाई कोई क्वेश्चन का जवाब उससे पूछा जाए तो वो उसको टालने के लिए जवाब दिए जाते हैं इस तरह. They are not real answers. So the real answer is that we get in statistical thermodynamics, which says that entropy is given by a function which is called S is equal to K ln M. Here K is a Boltzmann constant, so it's a constant, nothing to worry about it. Log natural is a function, and the only thing that varies here is M. What is this M? M is the number of microstates a system can possess for a given, you can say, macro state. So if you fix the macro state, and if there are inside that changes can take place within that macro state, then the number of state a system can occupy, that is M. And if you take logarithmic of that and multiply by K, you get entropy. Okay. So what it is giving an idea is that how many states a system can exist. That is what is entropy. Whether they are ordered or not, that is a different thing. Okay. So I gave you the example that in a class of, let us say, 120 students, if there are 150 seats here, you can sit in n number of ways. That possibility is you can have 150 C 120, and this is a very large number. This is how many ways you can sit in the room. Now if I increase this 150 to, let us say, 200, this value will increase. So if I put you in a bigger room, and my macro state is that there are 120 rooms, 120 students in this room. That's all. That is what I am measuring. What is the temperature of the room, pressure of the room? That is the thermodynamic properties. But when you are sitting in an n number of ways, that determines your entropy. So 120 students sitting in a room which has 150th seat capacity compared to a room where 200 seat capacity is there, in the second room the entropy will be higher. Right? So this is what we must, and that doesn't mean it's a disorder. You may, the bigger this room, you have big choices of sitting. You yourself choose that, okay, I will sit here, I will sit here. If there are only 120 seats and 120 students, you don't have a choice. Of course, still you can find how many ways you can sit, different combinations can be there. But if every student is identical, because in thermodynamics, what is happening when you're talking about air, every atom is identical. So if there are only 120 slots and 120 atoms have to be fit in, there's only one way you can fit in. So what is happening? As you increase the number of seats, you are giving more freedom to the gas. I may call it is a disorderness, but now the molecules are free to sit wherever they want. They are more free now. They say the concept of freedom is there. So instead of calling it a disorderness, I may call it as a more freedom they have. If you are sitting in this class and if you leave the class and spread over the whole campus, your entropy has increased. But you have got the freedom. Now you are sitting wherever you want to sit. You are sitting the person with which you want to sit. So we have to get out of this idea that entropy is a measure of disorderness. Okay, it's a measure of the number of microstates a system can possess. Now, why the nature is doing it? Because nature is moving in a particular direction. You see, there are certain things which are moving in only in one direction. There is one thing like time. It only goes forward, it doesn't go backward. Similarly, entropy always increases. And there is another thing, the evolution is also going on. And how does this evolution come about? It comes about by mixing. When different type of people, different type of things mix together, they create new things, new systems. Even socially, if you see, when you were sitting in a village, from there you move to a city, and from there you used to a metropolis cities, and you move to another country. As you keep on moving, your freedom and the expression of that freedom and the creation, all that creativity keeps on growing. When you are in a village, you don't have all those facilities to create new things, even if you have an idea. Okay, so basically, this is I see it as an evolutionary process. And this is more fundamental than the law of entropy. It is not because of entropy the evolution is there, it is because of evolution the entropy is there. So things are basically, entropy helps us to create new things, to grow, to evolve. Calling it disorderness, it doesn't appeal to me. Okay. And by the way, I would also like to tell you that there is a quotation in our Vedas which says Eko Aham Bahu Syam, which means I am one, I want to become many. Now this process, this one sentence describes this whole universe, that where this universe is going. This one sentence or a half a sentence, Eko Aham Bahu Syam, is telling that what is underlying this universe, and that from one to many or to multiplicity can be achieved only when you start mixing, you grow with that. So entropy वहां से आती है, evolution भी वहां से आता है. The first fundamental law which controls evolution as well as the time or as well as your entropy is this one sentence, half sentence, which says that Eko Aham Bahu Syam. This is what the Indian rishis picked up, understood, and conveyed to us. Anyway, so this is what is entropy. Now we want to study this reversible process, back to the reversible. So there is one law which says the entropy of the universe will always increase. Okay. Now, whether a process is reversible or irreversible, whatever is happening in this world, the entropy of the entropy of the universe, let me write here, is going to be greater than or equal to 0. And this entropy can be put up in two parts. The entropy of the universe is equal to the entropy, change in entropy of the universe is equal to change in entropy of the system plus change in the entropy of the surroundings. So the entropy of the system is also changing, entropy of the surrounding is also changing, and the sum of the two is the change in entropy of the universe. Okay. Now, when you are talking about a reversible process, then entropy of the universe remains same. There is no change in the entropy. So this is one way of deciding if in any process entropy of the universe is not changing, that process is reversible. Okay. So we have second definition here. First was if a system as well as the surrounding can be restored back to their original state, then the process is reversible. Similarly here, if in any process the entropy of the universe does not change, then the process is reversible. And what does that mean? The entropy of the system plus surrounding change will be equal to 0, which means that change in the entropy of the surrounding will be negative of change in the entropy of the system. So in any process, not that the system entropy is not changing. It is not that the surrounding entropy is not changing, but they are changing in opposite way and equal way so that their net change in entropy of the universe is 0. Then the process is called reversible. So for a reversible process, you can say the entropy of the universe remains the same, or you can say the increase in entropy of the surrounding is equal to the decrease in entropy of the system. It can be otherwise also. The decrease in entropy of the surrounding is equal to the increase in entropy of the system. The only thing is there's some change, sum of the changes is equal to 0. Now let us come to irreversible process. Irreversible processes are one in which the entropy of the universe will increase. Okay. And as I told you that all the processes are irreversible. So the entropy of the universe always increase. The reversible process we have talked about, they are only symbolic. They are ideal process. They do not occur in reality, but we can think about them and use them as our basis to compare the systems. Okay. Now, same equation, you have delta system, entropy of the system, delta S of surrounding, that will be greater than 0. And you can get this delta surrounding and it will be greater than negative of change in entropy of the system. You can interpret it in different ways, that for an irreversible process, increase in entropy of the universe is positive. Okay. But the system entropy can decrease or increase. Anything can happen. Similarly, surrounding entropy can increase as well as decrease, but their sum should be greater than 0. Okay. And from here itself, you can say that if there is a case where change in entropy of the universe is negative, then this process is impossible. Impossible or infeasible. And there are no exception on this, no assumptions on this. You get this and tell this. If the entropy is increase in entropy is less than 0 for the universe, you can immediately say that the process is not possible. You don't have to think about कि ये case होगा, वो case होगा, ऐसा होगा, वैसा होगा, नहीं. There are no sub clauses or clauses here. Okay, change in entropy equal to 0 of the universe, then the process is reversible. No other condition is required. And if the change in entropy is less than 0, change in entropy of the universe, you can immediately say the process is infeasible. No other check is required. Okay. So this is about reversible processes. Now we talk about what is a reversible engine. Okay. Now, engine, as I told you, is a device or a machine which is drawing heat from one reservoir and rejecting a part of it to a cold reservoir and doing some work out of it. And in itself, it is moving in a cycle. So what is an engine? It's a machine or a system, a closed system, which is operating in a cycle, receives heat from a reservoir at a hot temperature, rejects part of the heat to a reservoir at a low temperature, and converts the difference into work. Okay. So now what is a reversible engine? A reversible engine is one in which all these three things can be changed. So the arrows are changed. Now you are having this. If you have an engine on the left side, and you can also run it as a right side engine, that would become a heat pump. If it is, we'll call it as a heat pump. So it's the same engine you can reverse and it will start working like a heat pump. But then if these things will be same, this thing will be same, this will be same, and this will be same, then only it is a reversible engine. It's doing exactly the reverse of what it was doing. Okay, so this is a reversible engine. Okay. Now we come to the corollaries of second law. And the first one of them is that the Kelvin's Planck statement of the second law and the Clausius statement of the second law, they are self-sufficient. You get the point? If you want to talk about second law, you want to define the second law, then Kelvin-Planck statement in itself is sufficient. And on the other hand, Clausius statement in itself is sufficient. Both of them fully describe second law. No additional thing is required. And they are equivalent, which means that either both of them are true or both of them are false. Now remember one thing, I have said that still there is no proof of second law. Second law is a statement which combines all the experience of scientists in a simplest form. So whatever the scientists have seen, observed, experimented, they found that pertaining to this thermodynamics, they found that it can be beautifully encapsulated in a one statement, either Kelvin-Planck statement or a Clausius statement. Okay. But the problem is it is only telling what has been observed. So there is always a possibility that there are certain things which have not been observed, which are against the second law. So whenever in future somebody comes and finds a process and says that no, I have found a process in which the second law is violated, this law will be dropped. Simple. And same thing has happened. This is how science grows. In case of Newton's law, when Einstein came, Newton's gravitational law and Einstein's gravitational law, they are entirely different. What was the problem? Newton was talking about classical mechanics, or you can say low speed system, natural, which are common day systems. But when people started experimenting those things on high speed system, right, then Einstein found that there is another law for gravitation. It's not sufficient in itself. For Newton, the space and time were absolute. For Einstein, space also changes and time also changes. Here, one thing is coming to my mind, that if you read Indian Shastras or religion or whatever it is, there comes a term which is there we call of 5 elements. And out of that, Akash is one of them. So one is Prithvi, Jal, Vayu, Agni, and Akash. In Indian knowledge, Akash is treated as an element since time immemorial. If it is an element, that means it can be changed, twisted, manipulated. And that is what Einstein is saying. That space can be twisted. It can be bent. And it's not a joke. Einstein theories are being used to govern our satellite system. You see, the time, the rate, the time rate at which rate it flows on the ground is different when it goes to the space. So the clock which is in the space is running differently than the clock which is running on Earth. And scientists have to do the corrections for this difference so that their missile system does not fail, their navigation system does not fail. So time is changing, contracting or expanding, space is expanding or contracting, and that was there in our knowledge already. Anyway, so what Newton said, that was surpassed. Okay. What does that mean? That even this law can be surpassed. So let us remain open to it. Okay, somebody says that, okay, we have found a system which is breaking the second law. Okay, let us see. It is possible. Why not possible? Okay. But so far, nobody has found it. Okay. So we will continue with what has been said, that both these statements are equivalent. So if your Clausius statement is true, so we are not saying that both of these statements are true. Remember, by this way, we are not proving that both the statements are true. What we are saying that if A is true, B is true. If B is true, A is true. Right? So either both of them are false together or both of them are true together. That is their equivalence. Nowhere we are proving that both these statements are true. Okay. We should understand these nuances. We are not proving that second law is true. We are only proving that one statement is equivalent to the second and the second is equivalent to the first. They are both equivalent. Both can be false together. This is the only thing we are saying. So how do we prove it? Now, for proving, we are using the principle of exclusion, that what we will do is that we will assume that Kelvin-Planck statement is false. Okay. And then we will be able to prove that Clausius is false. In the second attempt, we will assume that Clausius is false, and then we will prove that Kelvin is false. So what we are proving actually, that if any one of them is false, the other one is also false. But we are not saying that both of them are true. If they are true, they are together true. If they are false, they are together false. Okay. So we begin with, we are assuming that Clausius statement is false. So what do we do? Now you look at this diagram. On the left diagram, this diagram, you have an engine on the left side. On the right side is a heat pump. So this is the engine and this is the heat pump. Engine is producing work and heat pump is transferring heat from low temperature to high temperature, but without doing any work on it. What did the Clausius statement say? It is impossible to construct a system which will transfer heat from a cold reservoir to a hot reservoir without any work being done on it. But we are saying Clausius is false. No, there exists a heat pump in which we don't have to do any work and it will transfer the heat from low temperature to high temperature. Okay. If that exists, you put them together. What do you get? And you make these two same. So your heat pump is such that amount of heat rejected by the engine to the cold reservoir, the same amount of heat is transferred to the hot reservoir. So what do you get in nutshell? Because this reservoir becomes redundant now, because you can transfer this heat from here to here. So whatever you are getting from the engine, that you put in the heat pump and it goes up. So what do you get? You get this system. If you combine these two parts, you get this system. And what is this system? It is receiving heat Q1 minus Q2 from one reservoir and doing the work equal to Q1 minus Q2. Which means it's a violation of Kelvin-Planck statement. Kelvin-Planck statement said that it is impossible to construct an engine which will receive heat from a single reservoir and do an equivalent amount of work without rejecting any heat to any other reservoir or a cold reservoir. Here it is possible. That means we had assumed that Clausius is false. It is proving that Kelvin is false. Okay. Now we look at the problem in a different way. Now we are assuming that Kelvin-Planck statement is false. Okay. So what is happening is, you look at this diagram on the left side. You have a heat pump here, which is transferring heat from low temperature to high temperature, and it needs some work. Now you are giving that work with the help of an engine which violates Kelvin-Planck statement. So this engine is exchanging heat with a single reservoir and giving work. And that work we are feeding back into the heat pump. You combine these two, what do you get? You get a heat pump in which no external work is required, and you can still transfer heat from a low temperature to a high temperature, which is again a false you can say violation of Clausius statement. So what have you proved? Okay, you have proved that if Kelvin-Planck statement is false, then Clausius statement is also false. So this is how you go about. You take an engine and you take a pump, right? In one case, you have a pump which is violating Clausius statement. In one case, you have an engine which is violating Kelvin-Planck statement. Combine the two, you will get an engine or a pump which is violating Kelvin-Planck statement or Clausius statement. So in other words, either both of them are false or both of them are true. Okay. And this is what it means is the equivalence of. Again, I repeat here, we have not proved that second law is true. We cannot prove that. We are only proving that two statements which describe second law, they are equivalent. Either both of them are true or both of them are false.